Hello everyone, welcome to the sixth episode of the series. In this video, we'll talk about zero matrix, identity matrix, and matrix vector multiplication. The last time, we talked about matrices, vectors, and some basic arithmetic, and we also introduced matrix transposes. And this time, as the title suggests, we're going to talk about zero matrices, identity matrices, and matrix vector multiplication. So a zero matrix is a matrix whose entries are all zero. And we usually denote this matrix by a zero, and we hope that the size is clear from context. And what I mean by that is that if you have a matrix A and we write A plus zero, what we mean is that we're adding a zero matrix of the same size as A. And it should be clear uh, that when we add a zero matrix to any matrix, it does not change A. In other words, A plus 0 is the same as 0 plus A, and they're both equal to the matrix A. Okay, so the next thing I want to talk about is the multiplication of a matrix and a vector. And the motivation comes from verifying a potential solution of a linear system directly using the augmented matrix. Now, recall that there's at least one way we can do this already, and that is by taking our potential candidate solution and plugging the values of xyz, or in general of the variables in all the equations. And if all the equations are satisfied, then uh, our choices of x, y, and z, in this case x equal to 2, y equal to 1, and z equal to minus 1, is indeed a solution. So to do the same thing using an augmented matrix, we first convert our linear system into an augmented matrix, and then we separate the two parts of the augmented matrix, one on the left side of the separator line and one on the right side of separator line, into two different things, which we call the matrix of coefficients and a vector of constants. The potential solution can also be collected into a vector. So this xyz equal to 2, 1, minus 1 is our candidate to be a solution, and we want to verify whether this is a candidate or not. Each row of the coefficient matrix A represents one equation. Let's focus on the first row. So when we originally learned how to verify a solution to a linear system, we would take values of x, y, and z, and we would plug them in each equation. And if they actually satisfied the equation, then they would be a solution for the system. Now, this act of plugging values of x, y, and z into, let's say, the first um, equation is equivalent to this middle expression in the series of equalities. Um, Note that this is the same as 2x minus 3y plus 4z, where we have substituted the values of 2, y equal to 1, and z equal to minus 1. And we write this thing as a product of this row vector, which is the vector of coefficients, and our potential candidate uh, a solution vector. And if this product ends up being the corresponding constant, then uh, it satisfies the first equation. And if it satisfies all the equations, in other words, if we take each of the rows and we multiply them with the vector 2, 1, minus 1, and it ends up being the vector of constants, then it is indeed um, a solution to the linear system. Okay, so let's look at multiplying a matrix and a vector more seriously. A matrix A and a vector V can be multiplied if the width of A is the same as the height of V. The product AV is another vector whose ith entry is the sum of the product of the entries of the ith row of A and the entries of V. What I mean by that is that if you take the ith row from the top, and if you multiply the first term of this row to the first term of the column vector, the second term of the row with the second term of the column vector, and so on till you multiply the last term of this row with the last term of this column vector, and then add them up, that sum is going to be in the ith row from the top in this column vector. And if the width of A is not the same as the height of V, the product AV does not make sense. So we can only define this product AV if the width of A is the same as the height of V. In other words, the number of columns in A is the same as the number of entries in the vector V. And the last thing I want to say is that the product of an m by n matrix and an n vector is always an m vector. So let's see a sample computation. So we're given a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're given a vector 1, minus 1, 1. And we want to compute the product of this matrix and this vector. And because this matrix has 3 columns and the vector has 3 entries, the product is defined and it makes sense. So when we actually try to compute this matrix, we first take the first row and we multiply 1 by 1, 2 by minus 1, and then 3 by 1. So remember, we multiply the first entry of the row with the first entry of the column, the second entry of the row with the second entry of the column, and the third entry of the row with the third entry of this column, and then add them up. And when we solve it, we get 2. Similarly, we do that with the second row. We multiply 4 with 1, 5 with minus 1, and 6 with 1, and add them up. And similarly, we multiply 7 with 1, 8 with minus 1, and 9 with 1, and we get 8. Okay, so now using the ideas that we've seen up until now, we can turn any linear system into what we call a matrix equation. So say you have a linear system of equations, then you can define a matrix of coefficients and you can define a vector of constants. Recall that the matrix of coefficients and the vector of constants are the things that you get by separating the 2 parts of an augmented matrix. And X can be the vector of all the variables. So you take all the variables that are present in the system of linear equations and you put them in a column. Then the linear system can be rewritten as the vector equation AX equal to B. For example, this matrix system represents a linear system of equations. Let's look at another exercise. So we're given this matrix equation, and we know that it represents a linear system, and we want to verify that XY Z equal to 1 minus 2, 1 is a solution to this matrix equation. Okay, so to verify that the vector 1 minus 2, 1 is a solution to this matrix equation, we plug it in instead of the vector XYZ, and then we just multiply the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9 with this vector. And we're going to first, multiply the first row with this column. So we're going to multiply 1 with 1, 2 with minus 2, and 3 with 1. We're then going to multiply 4 with 1, 5 with minus 2, and 6 with 1. And we're going to take the sum again. And then 7 with 1, 8 with minus 2, and 9 with 1. And when we take all the sums, we end up getting a 0, 0, and a 0. Okay, so the last thing I want to talk about in this episode is the identity matrix. So for a positive integer n, the n by n identity matrix is the n by n matrix whose diagonal entries are 1 and whose other entries are 0. And people usually denote the identity matrices by ID or I, usually hoping that the size is clear from context. And one of the things that makes the identity matrix so special is the fact that if you multiply a vector by an identity matrix of an appropriate size, it does not change the vector at all. For example, if I take a 3 by 3 identity matrix, that will be 1, 0, 0, 0, 1, 1, 0, 0, 1. So the diagonal has all ones and every other term is 0. And if you multiply it to the vector say 4 minus 1, 2, we're going to get back 4 minus 1, 2. And that's true for every 3 by 3 vector. And it should be clear from the definition, but the identity matrices are square, that is their height and their width are exactly the same. So with this, I would like to end this episode. Just as a recap, we talked about zero matrices, matrix vector multiplication, and identity matrices. And I will see you guys in the next episode. Up until then, happy learning.